Hello, Irene. Hello, Austin. Welcome. How you guys doing? I can't hear you. Your mic is muted, but I see your mouth moving, so I know you're talking.
Okay, I'm good. How are you?
I'm doing okay. I'm doing okay. Welcome. So you guys are our first students here. We got Austin too, and hopefully we'll get started in just a couple minutes. Oh, we got more. We got Erica. Hi, Erica. How are you? Actually, I can go ahead and there's a chat feature here. We can chat here. I have plenty of stuff to cover for you. Also, if you're on YouTube, just you can chat there as well. I'll go ahead and look. And then the YouTube is recorded, so you can always look at it afterwards. Looks like nobody's there yet. But anyways, we are here. Welcome, everybody. I'm glad you could join me. And so we are Siobhan. Hello. Welcome. I see your face. Hello, hello, hello.
Hello.
Hi. So we have a nice lecture on telescopes today, and I have something different from usual. I'm going to actually, I've been playing around with activities that you can do at home, and I have a couple. Actually, I had to fix my astrolabe. It was broken. I put brand new arrows on my astrolabe. Ooh, they're so cool. And I used it today to measure the altitude of the sun. So it's there's a safe way and there's a dangerous way. I want to teach you the safe way. But anyways, we'll do that later. I think probably next class. But this class, I have a little activity. It's very simple. It's not even really a difficult thing. It'll only take you a few minutes. But you get part of your participation points today are going to require you to do this activity. So I'll be telling you about that. All right, well, hello, everybody. Welcome to our classroom. And we have a lot of people, but you know, it looks like maybe a lot of people will probably just watch the recorded video later. And that's fine, that's what it is. But you guys are here and I'm ready to get started. So what I want to do is start off by making sure you know what we have to do. So you got the link on Canvas to be able to watch this video. And I actually also posted, let me just go ahead and, sorry, let me just share. Hold on one second. I can just do this. I got this. I got you, fam. Actually, you know what's so funny? I'm not as funny in a recorded video or just on Zoom. I think I'm more enjoyable when I'm in person. But anyways, I'm just noticing for myself, not for you necessarily. But anyways, yeah. All right. So anyways, take a look right here. I have overdue. Okay, so if anybody didn't do this yet, I don't know why I didn't put in the grades for that. I need to do that. But anyways, we have April 6th. That's today. You guys are supposed to do this solar observation makeup. If you didn't attend the solar observation, you need to do that. And then here's today's class. So here's a quiz that you got to take. Don't look at it yet. You get 2 tries. But here's the PDF and the PowerPoint if you want to watch that. And here's the link to our current activity. Our current video. And then if you click on this link, you get to the lab activity. Okay. So what I'm going to be showing you is an activity. It's a very simple activity. But what we're going to do is use page 22A in our lab manual. Does everybody have their lab manual with them? Actually, I don't know if I remember to bring mine. I'm going to look for mine for a second. So why don't you look for your lab manual? Oops. Okay. I don't have mine. Okay, hold on. I know where it is. I'll be right back. One second. Sorry, just listen.
I'm looking for mine.
Okay, just 1 second. Yeah, that's okay. You can do this afterwards, but I just want to show you what I want you to do. Aha.
Oh, it's not in there.
I got it. Okay, so we'll be using page 22A. And anyways, I'll show you guys how to do all this. So this is actually, make sure if you have your lab manual, this is going to be the page you're going to do your homework on, page 22A. And we're going to add some information there in just a few minutes. Okay. So meanwhile, welcome everybody. I see we got a couple more people. That's great. And that's neat. Okay, great. And you can chime in. I love to hear your voices. If you have a question, please chime in. Or you can type a message over here like, hi, everyone. I miss you. Right? Oops, I miss you. I miss you. Anyways, one day, oh gosh, I lost my camera. Oops. Okay, hold on. My other camera. I got this little thing that I rigged up, but there we go. Everything's good. Professional here. Here we go. 4:04. We're ready to go. So, are you guys ready? Any questions?
Yes.
Okay, you ready to go? Okay, so the program that you want to use is called Stellarium, right? And ideally, you download the program. If you can't do that, you should try to definitely download the program. You can get it on your phone, and you know, just to show you right here, let's see, Stellarium. Now I want to use this program with you. Unfortunately, with Zoom, apparently when I'm using Stellarium, it can't actually see things that I do. And so I can't use the program with you, but it's very close to what we're going to be doing. So instead of using the Stellarium program, they have, look, for Linux, Mac, Windows, and then they even have it for phones, right? So you have to get it off the Play Store or the iPhone store, I believe. But what I'm going to do is, instead of doing that, I'm going to go ahead and go to Stellarium Web. Okay, so this is actually a pretty cool program. I think I've shown you this before, right? Have I shown you this before? I pretty much have. I have, right? So you guys already know a little bit how this works. This little 3 lines makes that disappears. Also, if you hit the F11, you get a maximized screen, which is kind of nice, right? You can turn off the landscape and you can turn off the atmosphere, although the landscape shows you where things are. And so does the atmosphere. It tells you a little bit about the sunlight. So you can turn on the constellation lines, which is kind of cool, right? And this is about, you can change the time, right? So I can actually go back to like, oh, that's too bright. 7, I can see when the sun is going to set, right? Looks like it's about what time? 7:45 or something like that. Over here in the, oh, look at up there in the west. Look at high. What constellation is Venus in tonight? Can you see it? It's in Taurus, the bull. Okay, and there's the artwork for the constellations. Right, kind of cool. But actually, you're supposed to be able to identify these things. But anyways, Venus, you see, there's Venus right there. And actually, I don't want to look at the things, but I'll turn on these lines for a second. There's a neat thing we can watch is over the next, 30 to 40 days, right? The class is going to be over in 30 days, but let's say, actually, we'll be in finals week. But let's say I wanted to watch the track. I want to see how Venus is moving. And actually, it turns out all I have to do is just click this button and it advances time forward. I might need to move my clock, not that much, a few minutes forward just to not see the sun so much. But I can just advance Venus and you can see which way is it going. Well, it's going up, which, by the way, because of my orientation, it's hard to tell, but that's actually towards the east. That's the east part of the sky, right? Away from west, right, is going up. That would be away from west. That would be east, right? Does everybody see it moving eastward through the constellations?
Yes.
And that is what we call, anybody remember what it's called? The normal motion of the planets is towards the east. It's called prograde motion, right? But as you look right here, you'll notice Venus almost stops. And then I can't see, right? It's going to go away. I can turn off the landscape and I can see a little bit better. Actually, I'm going to turn off the atmosphere. That way you can see it really clearly. Oh, wow. Look at how bright it got. you can see that it's not moving, and then watch what happens. Oops, wait, sorry, not moving. And then it's not moving. Okay, now it's going behind the sun, right? Or in front of the sun, one or the other. Okay, so we're gonna actually talk about that next week a little bit more, but today, the key thing is I want you to be able to track the motion of Venus and then make a little track showing where Venus is for a number of dates up, over the next 40 days or so. So you're going to be using this page 22A to make a little track for Venus, right? What constellation is Venus in right now?
Taurus.
It's in Taurus, right? So we'd have to look at, actually the picture was kind of turned like this because Taurus was kind of facing up. The horns were going up like this. And so Venus was over here, but if you notice, it was moving up in this direction, right? And so I'm gonna ask you to show me the track of where Venus is located over the next 30 to 40 days, as long as you can see it, okay? And so you're gonna use that software to make a little dot, to show you where to put it, right? So it was over here when it started. You can put a dot down and tell me the date, right? And then it's going to progress across here. Show me the date, how it's moving across this. Take a picture of this and upload it to the assignment on Canvas, okay? Everybody understand? That's the extra little kind of activity for your participation today, okay? So meanwhile, we can use this for all kinds of cool stuff. We can actually go back to this thing and we can practice our constellations, right? Let's not look at the lines anymore. Hold on, I can't see. Oh, there we go. Okay, turn off the lines, right? And you guys know these things already, right? If you zoom out a little bit. If I take a look right there, what is the name of this star or object right here? This is the V shape for Taurus. What is this star?
Aldebaran.
Aldebaran, right? And you can click it and see if you're right. The eye of the bull, right? And then what's the name of this star? Well, it tells you Betelgeuse. You have to zoom. Which way? This Betelgeuse just always appears. Okay. Bellatrix disappears when you're a little bit further away, right? So Bellatrix, and Rigel, and what's this one?
Saith.
Saith, right? You can
Saith.
see that you're right? You can see it. It's actually a pretty easy way to test yourself. Okay, so we got Procyon. What constellation is Procyon in? Anybody remember?
Canis Minor.
Canis Minor, the little dog, right?
Little dog.
Minor, the little dog. Okay, so it doesn't show me the labels, but the program does. So that's why you want to use the program. And then what about Sirius? What constellation is Sirius in?
Canis Major.
Canis Major, right? And then we have a pair of twin stars right here. Who knows the name of the twin stars? The one closest to Procyon is?
Pollux.
Castor.
Pollux.
Pollux.
Very good. And then the one that's further is?
Castor.
Castor, and then you can see Capella because it's showing me, and then this we said was Aldebaran, right? You can also see some other cool things, like this is M42, which Erica says looks like a big heart for her, okay? And that's cool. And then we also see, things like over here, we see the Pleiades cluster, and Venus was actually right next to the Pleiades cluster. Actually, when you turn on atmosphere or off atmosphere, does it change? Not too much. Okay, actually not too much. It looks a little nicer without the atmosphere, doesn't it? Okay, but it's darker at least. Ooh, it's that. Oh, there goes a satellite. Cool, look at it go. That's neat. So tonight at 8:46, right, 8:47, you can see the Cosmos satellite go by, okay, which is kind of a fun thing. Okay, so you didn't learn a lot of these stars, but let's see. How about this one? Do you see, I'm going to rotate this guy just a little bit, pull a little away. Okay, so it's confusing without the land. Okay, let's go ahead and put the land back on. Can you see a backwards question mark here?
Yeah.
Anybody? Backwards question mark. So what constellation is the backwards question mark a part of? Anybody remember?
Is that Leo?
Leo the lion, right? Leo the lion. Good, good, good. And the lion is a regal lion. So what's the name of the star at the bottom of the backwards question mark?
Let's see, it's
You forgot.
Regulus.
Regulus, right? Regulus.
Regulus.
And then you need to know the tail star here. And the tail star is the nebula. The nebula, okay? So these are some stars. Now in between, look at Leo, Gemini, look at what's in between. Cancer is in between,
Cancer.
right? So Cancer is almost invisible. It's really hard to see, but there's a cute little cluster. Anybody remember the name of the cluster? M44, what is it? M44, not Praesepe, we used another name. You gotta look really closely.
Is that beehive?
That's the Beehive Cluster, right? The Beehive Cluster M44. So you can actually see it. It's in the middle of Cancer the crab. Okay, so in between Leo and Gemini, there's a little cluster in the middle of Cancer the crab, which is the Beehive Cluster. Okay, now down below, it's hard to see below, but down below, all by itself, there's a strand of stars right here, but it's all by itself. Anybody remember the name of the star that's down here? Its name is Alphard, right? So everybody say Alphard.
Alphard.
Okay, I got a few people. All right. Now, Alphard is a member of a big, long constellation. What's the name of that constellation? This is the head right here.
Is that Hydra?
It's Hydra, the water snake, right? Hydra, the water snake. So you can actually see, look at how long Hydra is. Ah, it's huge. Big, long Hydra, the water snake. Okay, it's actually much worse than that, but we're not worried about that. Okay, and then down here we have 1, 2, 3, 4 stars. What would that be?
Corvus.
Corvus the crow, right? Corvus the crow, and then right next to it, Crater the cup. It's difficult to see. They're very faint, right? And in this program, the size of the dot tells you how bright it is. And so a star that's brighter is going to have a bigger dot. A star that is smaller is going to have going to be a dimmer star. Okay. So what's the name for how bright a star appears in the sky? What's the word that we use?
Luminosity.
The luminosity is part of the brightness, but what's another name that we use? We have a scale called
Magnitude.
The magnitude scale. So a star that's brighter to our eye, what's the magnitude of Sirius? Anybody remember?
-1.5.
Like -1.5. See how big it is, right? It's really luminous, really bright in our sky. Okay, let's see. Let's go back out. Everybody remember, you see the Big Dipper right here? And then it's a little awkward. Oh, that's really awkward. Okay. I didn't mean to do that to you. Okay. It's things are a little distorted. If I try to make it flat, you can kind of see. This is the Dipper right here. You take these 2 stars and you take how many steps?
5.
1, 2, 3. It's not quite right, but it's because it's a little distorted. But this is Polaris right here. You can see that it's Polaris, which is the Little Dipper, right? Ursa Minor, right? And then Ursa Major. This is Zuby, right? But these are the stars of Ursa Major, right? Mizar is the bigger one, and Alcor is right next to it. Oh, it doesn't say that. Alcor. It's called Alcor, but anyways, you guys remember Alcor and Mizar? Okay, and then let's see. How about the W shape? Everybody remember the W shape? Where's W? See the W? What is that one? Cassiopeia, right? And then if you go from the middle of the W towards Polaris, you cross this star, you pass this star, and that is the little house Cepheus. And then around the Little Dipper, let's see if we can see it right now. Around the Little Dipper, in between the Big Dipper and the Little Dipper, and here's the head, is Draco the dragon, right? Draco the dragon. All right, so back to the Big Dipper again. Look at the Big Dipper. Remember the handle of the Big Dipper? It's curved, it has an arc. Now you can, oh, look at that. What the heck? I don't know what that is. Shooting star? I don't know. Okay, and if you follow the handle of the Big Dipper, what happens? You arc to?
Arcturus.
This is already showing us. And then you spike to? sideways spike to spica. What constellation is Arcturus in? Remember the name of it? Called Boötes the herdsman, right? And what's the nickname for it? Here's the bottom part that you hold. There's a big
Oh,
scoop.
the ice cream cone.
The ice cream cone, right? The ice cream cone. And then Spica is a member of Virgo, the maiden. Okay, and those are our new constellations that we learned. Okay, so you can practice your constellations, and actually, if the weather gets clear, you want to look at the sky as much as you can, and then so I hit F11 again, and it takes it out of the full screen mode. Okay. All right, so you have two things to do. You're watching the lecture or listening and participating, and then you take a quiz, right? And you do that on your own after you're finished, and then you have to do this participation thing where you use Stellarium to track Venus over the next 30 to 40 days. Okay, so that's your assignment for the day. And now let's go ahead and look at your slides. Okay, so I see more people. Hey, Grant, how you doing? Everybody else, who else? I'm missing a bunch of people. Drelin, yay. Okay, cool. Siobhan, all right. I miss you. Oh, I wrote that. Never mind. Okay. And anybody else? No, nobody's watching the stream. Okay, so let's go ahead and get started then on the PowerPoint. And so I'm going to go ahead and I took a clue from myself. I looked at this PowerPoint. It was old and tired, and I'm like, time for a new PowerPoint. So I updated it, added some slides, made it fresh and informative. It's all on Canvas, by the way, so take a look. Here we go, telescopes. How do they work? And this is a more theoretical thing for you to learn. So what you want to do is find some paper, or in the back of your lab notebook, you're going to go ahead and take some notes. This is your telescope lecture. So I'm going to tell you some theoretical things about telescopes that you need to know. And before very long, I don't know if it's next week or the week after, you have to take a quiz on how telescopes work. So what I'm teaching you tonight is supposed to cover all of that material. You'll be totally ready. I should mention, by the way, there is a study guide on Canvas. But it's also everything that you see in this slide set. Okay, so we can look at that afterwards if you want. Okay, so number one, let's take a look, right? What's our slide sets? We've got a little bit of history, not very much, just a little bit. And actually, I put a couple of different history things in. So the very first invention, and then later on, Isaac Newton invented a reflecting telescope. We'll tell you a little bit about that too. And then we'll tell you about the theory behind it. What's the physics? What's the science behind it? This is really fun. And I found some new cool ways to share this with you that I'm super excited about. I've never seen such cool simulations. I'm so excited, and they're totally gratuitous and fun. But anyways, it just took coronavirus for me to find these things. Actually, and being able to teach you online means I can use more computer type of tools than I usually would. Normally, I'd have to just lecture in the planetarium with that awful fluorescent board. I wonder if they're going to change it now that there's coronavirus. Eventually, we're going to get past this, right? Is everybody hopeful? We're going to get past this. You just got to be strong. Okay, so a little bit of history you need to know. The inventor was not Galileo. Galileo Galilei was just one of the first users of the telescope, but the inventor was Hans Lippershey. He's from the Netherlands, Holland. And it was 1608, he invented the first refracting telescope, refractor. So the word refract is an important word you need to know. A refract means to use lenses to bend the light. Refraction is bending the light. And I'm actually going to show you a little more detail on that because there's some cool little things that you may or may not know about refraction. But Galileo heard about it very quickly, it turns out. And when he heard about the first telescope, and by the way, the first telescope was not made for astronomy. What was it made for? Does anybody remember? It was made for like military use, right? To spy on your enemies, or maybe for people at sea, for a ship captain to have to spy land and things like that. But it was not really at all meant to be an astronomy tool. And Galileo was like, well, yeah, let me look up at the sky and let me see what I can see. And so, of course, we're super grateful for Galileo for doing that, because he kind of revolutionized the concept of what the universe is. Up until then, it was just, this time when the sun wasn't there. And then it became something much richer. And it actually told us about our place in the universe, which was even cooler. So Johannes Kepler, anybody recognize that name? He was the assistant for Tycho Brahe, and actually went on to invent his own type of telescope, which was actually a pretty nice design. It made really crisp images. Galileo's telescope was a little primitive, actually, but anyways, don't worry about that. So here's the basic idea. So you have in a refracting telescope, you have a lens. And actually the coolest thing is to understand that your eye is actually a kind of lens. And I found the neatest simulation, actually, I want to show you. But anyways, before we go any further, you want to take a look right here. You have a lens. This is called a convex lens. I'll show you in a minute the name. And the rays of light are coming in, they're parallel to each other. But as soon as they hit the glass, they start bending. And the word bending in physics is refract. And if you notice, at a certain distance, they seem to come together. They don't stop there, they keep going. But for a moment, they're in one spot. And that's called the focal point, right? You're going to need to know that. Again, these words are going to come up in a moment, so don't worry about that. You may have noticed, if you look, if you use like a single magnifying glass, if you hold it out at arm's length, if you look through it, it flips everything over. Have you ever noticed that? And actually, this turns out is what's going on inside of your eye. And I have the coolest simulation. Take a look, click this right here, and the link should work for you too. The optics of the human eye. Oh my gosh, they did such an awesome job on this. Awesome. Okay, so you take a look right here, and actually, this is the front of your eye. You can't tell. Let's turn on the eye. Look at this. Isn't this cool? Can you guys see the eye now? Everybody see the eye?
Is
Yes,
it
no,
different
maybe?
from the-
Okay, you see an eye, right? So this is the eye, and the back of your eye is called your retina. And the light comes through this opening, the pupil, right? And there's this lens that's going to focus the light. Now, for a person with normal vision, right, an object that is far, they can use their muscles to change the shape of the lens, and they can cause the light to come to a point at the retina. They have focused the light. Does everybody see how that happened? You have to change with your muscles the shape of your lens, right? Called accommodation. If I move that object close to you, right? You see, no matter where it is, right? There's a certain muscle strength or accommodation that I need to make in order to make it focus. If the object is very close, then your muscles have to get, really change the shape of the lens, okay? Now, some of us have to wear glasses, right? And it's no big deal, but it turns out that if you wear glasses, let's say you're nearsighted, let's try to understand what that means, right? If you're nearsighted, what does it mean? Your muscles are able to change the shape of your eye one direction, but not the other direction quite as well. And so if you focus, right, you're able to focus the light, which is close from an object that is close to you. But if you're nearsighted and you try to look at something that's far away, no matter how hard you try, watch what happens, right? You can never quite get it to focus, right? It doesn't quite make it. So you need some glasses, and you put on glasses, and the glasses make it work, right? The glasses have the effect that it allows your eye to now focus it properly on the back of the retina. Isn't that neat? Oh my gosh, I love this app. Okay, now, what if you're farsighted? Now, if you're farsighted, it turns out the muscles are different, right? They can accommodate when you're, the focus, they can accommodate when your eye is far from the object. But if the object moves too close to you, right,
Sean,
then no matter how hard you try, you can never make it come to a point, right? You can never focus it. And so again,
Sean?
you need glasses. right? You need to put on glasses, and then the glasses correct for it. Isn't that neat? Okay,
Uh,
so
Sean?
anyways, that is question.
Yes, I can't see any, I hear what you're saying. I don't see anything of what you're showing.
Oh, shoot. Oh, gosh, you guys, you didn't
I
see.
was looking at the eyeball at the bottom of the screen on
Oh,
the slide.
shoot. Oh, man. You didn't see
Yeah.
any of that. Okay, hold on.
I mean, I know what you were talking about, but
No, you didn't see it. Okay, hold on.
oh,
Darn it. Okay, here we go. Now do you see
there it
it?
is. Yeah, oh
Oh,
yeah.
gosh. Oh, gosh. I keep forgetting. I failed again. I got to remember to do this. Okay, that's why I asked if you guys saw the eyeball, but none of you saw the eyeball. This is the eyeball. Okay. All
I-
right. Let's try it again. I'm going to do it again because it's worth it. Okay, sorry about that. It's a little repeat. But take a look right here. So if I have normal vision, if an object is
Mhm.
close, I can use my muscles and I can make the focus point come to a point right at the retina. If
Mhm.
the object is far, I have to use my muscles, but I use my eye muscles and they're able to accommodate or bring the focus right to the back of the retina. If I'm nearsighted, something happens, right? When the object is far, no matter how hard I try, I can never make it quite get to there. If the object is close, on the other hand, I'm able to get the focus and I can actually get it to work. So when you're nearsighted, you can focus an object, you can put the light from an object that's near to you can be focused. But when you try to look at something far away from you, no matter how hard you try, you can't quite get the lens to work. And so you need glasses. And the glasses will make it so that the focus point goes right to the retina again. Okay. Okay, if you're farsighted, it's the opposite, right? If you're farsighted, you can focus on things that are far from you. You can make that come to a point all by yourself. But if the object gets too close to you, right, then no matter how hard you try, you can't make it come to a point, right? I'm trying, and it's just not working, right? It's still blurry. So I need glasses as well. And so they can correct for this vision. And now you can see, okay, so sorry about that. Let's try to go back to the slide set now. Okay, now you've seen it. I know what to do now. I have to just remember to do that. Okay, so these are the two types of lenses. Please write down convex lens and concave lens. There's two different kinds of lenses. And if you look at the picture, the light is coming from the left-hand side. And if you notice in the top picture, the light comes through. Does everybody see the two lenses, by the way? Let me just make
Yes.
sure. Yeah, okay. The light is focusing into a point, right? And this point is called the focal point. The distance from the lens to this place right here is called the focal length. You should write that down. The focal length is the distance required to make the light come to a point. And so depending on the lens, that might be a different amount of distance. Actually, the experience you have is with the eyepieces. You might remember we had a bunch of different eyepieces. And those eyepieces are 25 millimeters or 18 millimeters or 12.5 or 9. That's the distance required to make the light come together to a point. That's the focal length of the lens. Now, concave is a little bit different. The rays of light come in, but instead of coming together, they spread apart. They go away from each other, and they go away from this point over here. This is the focal point for this thing. It's a little bit strange, right? But they go away, they diverge. That's the word go away from. They diverge away. It spreads instead of focuses. But it's still considered to be a focal length. I know it's a little confusing, but the distance from this point that all the light is going away from to the lens is called the focal length. Okay, so you have just two pictures. One convex brings the light together. One concave spreads the light apart. Move this up. Okay. So why can't you see an object that is far away? And the answer is because it's too tiny, right? If you make an image on your retina that's too small, you just can't see it, right? So if you tried to take a picture of a dime from 50 meters away or half a football field away, you wouldn't be able to see anything, right? It's just too small. But you can actually use light, you can bend light and use lenses to be able to do this. Okay, so I'm going to click the link, and this time I'm going to remember to change my share. Sorry about that. And I'm going to go to this application right here. This is really fun. Oh, I love this one. This is really cool. You're going to like this. And then I'm going to go back to the other one for a second too. But anyways, this is the beginning. I have a laser beam right here. It's a little more than you need to know. And I can actually change the way the laser comes in. And I have on the top, the white area is air, and on the bottom is water. But I can actually change that, right? I can turn it into glass or something else. I don't know what. Anyways, you don't have to learn much about this. It's just the key thing is that the ray of light comes in and it doesn't go straight. What does it do? It changes
Bends.
direction. What's the word for changing direction? It's called refraction. That's the word, refraction. So refraction means bend. So one of the things that you want to understand is we measure this angle here. Actually, you don't need to know all that. It's called the angle of incidence and the angle of refraction and all that stuff. But it doesn't matter. It does, you know, whatever. I've got like a 60-degree angle right here, but when it comes out, it's only 40 degrees. Okay, it's a smaller angle this time. And again, you know, we're not studying all the physics here. But do you notice something else? There's another ray that's very faint right here that seems like it's just bouncing. Does anybody know what it's called when light bounces? When light is bouncing, like when you look in the mirror, light is bouncing. What is it?
Is
Called
that
Reflection?
reflection, right? So reflection of light is another principle, okay? So now what if I switch this to air? So it's air and air. What happens to the laser beam?
continues?
It goes straight ahead, right? It doesn't get bent. It only gets bent when, you see how it's bending? When you change the material. And the reason it turns out is because the light is changing speed. It's slowing down when it goes into this material down here. Okay, you don't have to know that, but I'm telling you anyways, okay? All right, now, something more fun. There's something called a prism, right? It's actually pretty neat. There's a prism, for example, and you can take the light and you can shine it in. What happens, right? It bends first when it goes from the air into the glass, and then it bends again when it goes from the glass into the air, right? So that's interesting. This simulation actually has the ability to put in white light. And what color is white light?
All the colors.
All the colors, right? So if I put in white light, let's see, put in white light, okay. Put in white light, are you ready? Okay, do you see something happening? What's
Rainbow.
happening? What comes out of the prism?
Rainbow.
What do you see? All the colors, right? So what's going on? You should write this down. Is the amount of bending of the light depends on the color. And we're not going to study this too much, but just you want to be aware. This is something that you have to be aware of. It's the reason why we have rainbows, right? Different colors bend different amounts. So when I look at the original direction and the final direction, which color bent the most? Which color bends the most? So what are the colors of the rainbow? Who knows the colors of the rainbow? Roy, G, Roy G. Biv. Which color bends the most?
Blue and indigo?
The indigo, the violet. The violet actually bends the most. Which color bends the least?
Red?
The red bends the least. So isn't that interesting? Do you remember, anybody remember anything about frequency? Which color is the highest frequency?
Violet.
Violet. So higher frequency bends more. Lower frequency bends less, right? So in principle, this is kind of a neat idea, but this is the reason why we have rainbows, right? And it's getting it'll get a little complicated, but you guys want to see this? It's pretty cool. But actually the question, why do we have rainbows, right? Now, I actually think that this one is as cool as it is not as good as this one. Can you guys still see the eye?
Mm-hmm.
Okay, so I'm going to go up here to light and I'm going to show you rainbow. This is fun. Oh, this is so fun. So this is white light that's coming in. And which color is bending the most, the violet or the red? The violet bends more, right? And you can actually see all of the colors of the rainbow are in between, Roy G. Biv, right? Okay, so the color that bends the most is violet. The color that bends the least is the red, okay? So anyways, let's zoom out. If I'm looking at a rainbow, I want you to try to understand it's not just one drop in the sky, it's all kinds of drops all over the place, right? There's droplets here, there, everywhere. There's higher drops and there's lower drops, right? So what you want to try to understand is what happens is that this is the direction that you want to be, let's say to see a violet. Actually, let me start with this one. Let's start with the red. So the red, let's say that this is the droplet that red light is coming from. I'm standing right here. I'm going to stand right here. That's where I'm standing, right here. Okay. And then I ask my question: which droplet do I see the violet coming from that droplet or red? If I stand right where the tip of my arrow is,
Red.
I see red, right? So how do I see violet? Well, violet, you see, seems to come from lower in the sky. I need to make an angle like this. So there's going to be droplets down here that are going to make violet light that I can see over here. So when I look at a rainbow in the sky, which color do I see higher on the top and which color lower on the bottom? Do you know? I don't know if you've ever looked at it carefully, but I'm going to actually, I know you've seen many rainbows. I know you have, right? Or at least pictures of them. But what does it look like? A real rainbow, not a, no, I mean a real, look at that beautiful rainbow. You see it? Which color is on top?
Red.
Red is on top because it appears to come from higher in the sky because red doesn't bend as much. The violet appears to be lower in the sky. Now, has anybody ever seen a second rainbow? A second rainbow? It turns out if it bounces one more time, you get a secondary rainbow, right? Isn't that cool? So you get the primary rainbow and you get a secondary rainbow. Now it's much fainter, but something funny happens. I can't see the spread. Where's my spread here? This is a little messed up. Oh, this got messed up. Something's a little messed up. Oh well. Zoom in. Spread. Okay. Okay, the simulation got a little messed up. So here's the problem. So it doesn't show you very well. But the secondary one, actually, when it bounced the second time, what happens is the colors get reflected and they're actually going to be reversed. So the violet will be on top and the red will be on the bottom. Okay, so let's look up a double rainbow. Double rainbow. You might be like, why am I talking about rainbows, right? But it turns out to be relevant to, actually I saw a double rainbow the other day. Me and my wife, we were watching it. Okay. So you can see, so the red is on the top for the primary. That's not right. That's actually doesn't look right. Let me see. I don't want to see that. Let's see this one. No, I don't like that one. That's ugly. It's right though, but it's ugly. How about that one? Can you guys see? So red is on the top. And on this one, violet is on the top. But this is the primary rainbow. And this is the secondary rainbow. See how much weaker it is? Because it has another reflection. It loses some light every time it reflects. Okay, so this is a little bit gratuitous. So you might be asking your question, why do I need to know this? And the answer is because this is something that people found happened to telescopes. In fact, even Galileo noticed it. And it's a problem with lenses. The lenses start to show colors. And we have a name for that. It's called chromatic aberration. Actually, I'm going to go ahead and write that down for you because you need to know that name. So the word, when you look through a telescope and the colors are focusing, they don't all focus in the same place. So which color bends the most? You remember?
Violet.
The violet. Okay. So if I put white light through a lens, right? If I put white light through a lens, then what happens, right? Well, the light focuses. It comes to a point. But it turns out that the violet comes to a point that's very close because it bends so much. This is the violet focus. And the red doesn't bend as much, so the focus is going to be over here. Are you guys getting the idea there? That the different colors bend different amounts. This is the red. And so as a result of that, what happens? You can't make all the colors focused. You can't do it. Not possible. So this is a flaw with all lens systems. The bigger they are, the more the flaw shows up. And it's called chromatic aberration. And it's a problem with telescopes, right? So if you want to use a big telescope, you're going to really notice that you start to get rainbows. You may have even seen this. I don't know if you've ever noticed with like overhead projectors sometimes will show a rainbow. And it's called chromatic aberration, okay? So not all the colors focus in the same distance. It's not possible to focus all the colors in the same place. Okay, all right. So everybody good? All right, let's go back to our slides. Okay. Okay, so if you had a bigger eye, you would collect more light. So in effect, what a telescope does is it makes your eye effectively larger. And that way you can collect more light. So there's two main pieces of every telescope that you have to be aware of, right? There is the front lens, which is called the objective lens. In a refracting telescope, that's called the objective lens. Or, what you need to know about, the primary mirror, right? Which is the mirror that catches the light in a reflecting telescope. And then you need something to make an image out of it, and that's the eyepiece, a lens or a set of lenses. Okay, so every telescope has an eyepiece, but you have two different kinds of telescopes. We have refracting telescope, which only have lenses, and a reflecting telescope, which uses a mirror to collect the light in the first place. Okay, remember these slides are on Canvas. If I go too fast, you can always just go look at them again, or you can pause. You can go watch the video again. You know, this is actually the benefit of the video too, right? If you miss something, you can go back and rewind it later. Hopefully not after. I mean, after you watch the live one. Okay, so the objective, it's a little bit repetitive. I actually even trimmed it and I'm still being repetitive, but let's read it again. The objective lens collects light from a distant object and brings that light or image to a focus, to a point or focus. An eyepiece takes the bright light and then makes an image out of it so that you can see it, right? It's kind of like a magnifying glass. So it takes a smaller thing and spreads it out so that you can see it. So it looks bigger, like a magnifying glass. Anyways, you have objective or primary mirror, and you have the eyepiece. This is the two main pieces. Okay, so we just want to understand, how do you put them together? How do you make a useful telescope? What's the principle behind that? Okay, and we're not going to get too deep, so it's just really just a simple kind of procedure here. So here is a very simple diagram. Please draw this diagram. This diagram shows a simple telescope, right? So over here, the big one is the objective lens. The light is coming in from the right-hand side. And you'll notice that the distance from the big lens to this point is a capital F, right? It's definitely not the same as the distance here. Okay, so you want to understand that different focal lengths can have different lenses will have different focal lengths. Okay, so it's not necessarily true, by the way, that a big lens has a bigger focal length, but it's generally going to be longer than a smaller one. Generally true. It has to do with how curved it is, but we're not going to talk about that too much. The more curved it is, the shorter the focal length. The less curved it is, the longer the focal length, right? So you can actually make big lenses with very long focal lengths, or you can have big lenses with pretty short focal lengths. But anyways, they have different focal lengths. Okay, so big F right here would be the focal length of the objective lens, and little f would be the focal length of the eyepiece, right? All right. So there are actually, in order to do its job, two major jobs that a telescope has. One is how well does it collect light? And the other is how much does it magnify the image? So what does the word magnify mean? You guys know what that means?
To make larger?
Make it larger, right? So actually it turns out you can have fractional magnification. Don't worry about that. But anyways, that's a little strange. With the telescope, it's making it larger. So how much magnification do you get? So there's a new word here that you haven't seen before. Please write that word down. The aperture. Aperture. By the way, for 40 years of my life, I misspelled that word. I thought it was aperture, but it's aperture, which is the opening at the end of a telescope or a camera. It's used in many places, it turns out, but it's the opening that lets light in. Okay, the opening of a telescope or a camera that lets the light come in. Aperture. So you want it to match the size of the objective lens or your primary mirror, right? You don't want it to be too small because then you'd block the light from coming in, right? So you want it to be as big as you can. And so basically the size of your objective lens or your primary mirror determines the size of your aperture. And then your magnification, we'll talk about how you do that. All right. So aperture, right? The telescope's ability to collect light is directly related to the size of the lens or mirror, or the opening that is used to gather the light. The area of the circular opening is pi r squared. Maybe you recognize that formula. Everybody recognize that formula?
Mm-hmm.
Okay, so I'm going to actually give you a simple example. A telescope that is 10 times as large as another one has an area which is 100 times as large. Now, I actually feel like I need to give you some better examples. So can I actually, I'm going to show you a couple of examples. You need to be able to do this, okay? So there's a formula here that the area of a circle is pi r squared. I actually don't care about the pi. I don't care about it. I mean, you can leave it there if you want, but it's mainly the r squared that I'm thinking about, okay? So if I have a telescope, and maybe that telescope has an opening which is, I don't know, 10 centimeters, right? 10 centimeters. And I want to compare it to another one that is, 30 centimeters, right? 30 centimeters across. Which one has a bigger area? I mean, that's pretty easy, right? I mean, I don't know why anybody would even question that. But you need to know more than that. You need to know, obviously this has more area, but how much more area does it have? And the answer is, anybody? How much more area?
800, right?
How much?
800 square centimeters, whatever.
300?
900 minus 100? 100?
It's 9 times as much, right? So the reason is that in one of them, you're doing A equals pi times 10 centimeters squared. And in the other one, you're doing pi times 30 centimeters squared. But I don't actually want you to do all the math, right? Don't do the math. What I want you to think about is the first time you did pi r squared, and then when you went from 10 to 30, what happened? You multiplied by what? And you need to figure out what factor did I multiply by?
3.
And there's 3. Grant's holding up 3. Okay, so my new area is pi times 3r quantity squared, right? So what gets squared, the 3 or the r?
3.
Both of them, right? Both of them, right? So pi and 3 squared is 9, and then r squared. And you bring the 9 out in front, and you get 9 pi r squared. Well, pi r squared was the original area. So you just got this extra factor of 9. It's 9 times the area. Okay, so when you figure out the factor that you multiplied the diameter by, or the radius, because radius and diameter are related to each other, then you square that number to get the amount of area that you increased. Okay, any questions on that? That's usually the hardest part. So if you get that idea, then you're fine. Okay, so maybe if you go back to this question, right? If it's 10 times as large, that's why it becomes 100 times the area. So 100 times the area means what? How much more light do you get?
10 times.
If you have 100 times the area, you get 100 times as much light. That's the idea. Okay, so why is a bigger opening better? You get more light. Okay, so we'll talk more about that in a few minutes, but that's the basic idea. Okay, so we want to get more light because then we can see stuff. We can see dimmer things. We can see things that are hard for our eye to see by itself, but with the telescope, by collecting more light, we'll be able to see them, right? They won't be too dim. Okay, so here's the magnification formula. Please write it down. The way it works, oops, sorry, the magnification formula. The magnification of a telescope is the ratio of two focal lengths, right? The focal length of the objective lens divided by the focal length of your eyepiece. Okay, so you can write down this sample calculation, right? This is our Celestron 5SEs. The focal length, I didn't, so it's, or primary mirror. The focal length is 1250 millimeters, right? If you divide that by our 25 millimeter eyepiece, so which eyepiece do we always start with? You guys remember that? Or maybe not?
No, no.
If you forgot, then please write down. We start by using the 25 millimeter eyepiece. Why? Why do we do that? Okay, we're about to find out, right? Does it give us the highest or the lowest magnification? Which one? Okay. So we always start with the 25. If you use the 1250, which is what it is for our Celestrons, right? It never changes. And you divide by 25, you get a magnification of 50. It's a 50x, 50 times as big. Okay. So I'm going to stop this for a moment and then ask you a question right here. I'm going to write the magnification formula. Objective divided by the eyepiece. Okay. And we always have 1250 for the Celestron, but what if we put in a different number? Okay, so let's see, I got to slide this down, right? So what's going to happen? We know if you put in 25, what do you get? Oh, you can't see. Okay. You put a 25 in, you're going to get 50x. But what if you put in a smaller number, right? So the eyepieces that we have, here's what we got. We got 4 of them, right? We've got the 25 millimeter, right? We've got the 18 millimeter. We've got the 12.5 millimeter and the 9 millimeter. Okay, so we only have smaller ones now, right? What happens if you divide by a smaller number? What if I put in 18, for example? Oh, 18 millimeter. Do you get a bigger or a smaller answer? Yep, okay, your answer gets bigger. And if you do the calculation, you do the math, you get 69. We're going to call it 70. It's close enough, about 70. Okay. So you see what's going to happen. The smaller the number you put in, actually, what if you put in 12.5? What do you get?
10 times?
You get
No, 100
12,
times.
1250 divided by 12.5, you get 100x, right? You're going to get 100x. What if you do this one? So this was 50. This was 70. This is 100. Look at 100. It's twice as big. Why was it twice as big? Because 12.5 is half as big, right? You're dividing by half the size of the number. So what do you think this one's going to be if it's half as big? Oh, you can't see it. Okay, there we go. 140. Okay. You don't want to use your mic? You don't have a mic? You don't have a mic. Okay. I can see, I can read your lips. I read your lips, Grant. Okay, so everybody see that then? So we got, what happens? The smaller the number of the focal point, the focal length of the eyepiece, the larger, oops, what am I doing? 140x. I'm getting a little confused. 140x, sorry about that. The smaller the focal length of your eyepiece, the larger the magnification will be, okay? No, we can't hear you, Grant. I thought we can't. No, we can't hear you. No, no problem. But we can read your message though. If you write your message, we'll hear you. Okay. You can hear us though, so that's cool. Okay. All right. So that's that. Let's go back here. All right. So if you've ever noticed, if you look through a magnifying glass, you might have noticed everything gets flipped over. And that's actually kind of interesting. You don't have to worry too much about that. I just want to remind you that that happens. There is a little bit more to eyepieces. They want to do, what did they use for, right? They allow you to make to change the magnification. If you want to change magnification, you don't change the primary mirror, right? That doesn't make any sense. You change the eyepiece that you're using. So you change the eyepiece of your telescope and you change the magnification. You want to get a nice sharp image. Your eyepiece is going to help you to do that. But also, it turns out eyepieces have the ability to be manufactured to have what is called eye relief. Okay, so there's a distance between the lens and where your eye should be. And so they make lenses on purpose where you need to pull your eye back a little bit, which is really great for people who wear glasses, for example, because then they can wear their glasses even when they're looking through the telescope, okay? So if your eye relief is very small, then you won't have enough room for you to wear glasses. You'll have to take your glasses off. There's another thing, if you remember, you should write down, if you don't already know it, field of view. What is the field of view? It's the amount of the sky that you can see in degrees, right? And there's two different versions of it. One is how much you're supposed to be able to see. And then the other is what you actually can see. But don't worry about that. We're not going to worry about that. But anyways, that's what the word means. So if you buy an eyepiece, when you look at it, it'll say what it's supposed to be is this. But when you look through it, you actually get a little bit more. It turns out if you look through a real eyepiece, depending on the eye relief, you actually have a little room to move your eye back and forth, left and right or up and down. And that gives you a little more sky view than you should be able to see. You don't have to keep it right in the middle of the eyepiece, in other words. Okay, don't worry too much about that. We also can use filters. And actually you have looked through a solar telescope. When you look through the solar telescope, we used a filter like this that blocked most of the light from coming through. And then, and actually there's other kinds of filters as well. Okay, so we won't use, I don't think I have any questions on your quiz on that, but there's something that's kind of fun to play with. Why do you use a filter? Actually, just to understand, what does a filter do? Like, for example, this red filter. What color do you see? Does this white paper look red, or what color does it look when you see the light?
Pinkish.
So if you shine white light through a red filter, what happens? What do you see? What color do you see?
Pink.
Pink or red, right? Let's just say red. Easy enough.
Okay.
Yeah, it could be pink, right? Well, no, you don't see pink. Sorry, you see red. Sorry. If all the light comes through this red filter, only red light can get through. So this red filter only allows the red light to come through. But you might know that in computers, red, green, and blue mixed together make what? Do you know? They make white. If you've ever put a little droplet of water on your screen of your phone, you might have been able to pick it up, actually, that they have little tiny phosphors of green and red and blue. And together they mix and they form white. So what is this filter doing? This filter actually lets the red through, but it actually is doing something else. It's blocking the blue and the green. And so another name for these filters is it's a subtractive filter. It takes away light. It only lets through some of the light. And so that's something that we're doing with the filters. We're blocking some light and letting other light through. So it turns out this blue filter could be used if you look at the planet Mars. If you want to look at the poles, the ice caps of Mars, it turns out the blue one is really good. Not the red one so much. Because what color is the planet Mars? Anybody know? It's red, right? So it turns out if you use a red filter, it doesn't really do much for you. But if you use a blue filter, most of Mars is going to look dark because there's no red light. But the ice caps, which are white in color, right, are going to reflect the light, and they're going to have some blue light there, and they'll kind of show up. They'll really pop, right? So sometimes people use these filters to help see features, you know, that otherwise you wouldn't see. Okay, forget that. We don't have to worry too much. All right, so we mentioned the two types of telescopes, refracting or refractors, and reflecting or reflectors, right? So the main collector is what defines it, right? If you have a big lens that's collecting the light, it's called the refracting telescope. If you have a big mirror that's collecting the light, it's called a reflector. Okay, they both do the same thing. They collect the light and then they focus the image. Same thing, right? Okay. So how do you make it, right? Actually, I'm going to show you some pictures. This is an actual very primitive diagram. And it's just like the one I showed you before, but now you have a tube holding it all together. Actually, what's the name of the tube? It doesn't say that. Okay. This tube, I'll tell you in a minute, is called the optical tube, if you want to write that down. The tube that holds all of your optics together is called the optical tube. And so it holds the lenses in place, right, that you need. It's a very simple design, okay? This is a little bit different, but it turns out that in the old days, this was the only kind of telescope originally. And they tried to make them big, heavy, the heavier it becomes. And consequently, they had to build these giant heavy tubes to hold it all together. So the tubes, the optical tubes became so heavy that they became the reason why we stopped making them any bigger. You just couldn't make something strong enough. It was just became too heavy, you couldn't lift it. So once the telescopes became too big, it turns out it didn't make sense to make refracting telescopes anymore. It was much cheaper and lighter to make a reflecting telescope. So the largest telescopes in the world today are all reflecting telescopes. We do often see these refracting ones in high-end astrophotography, okay, which is kind of an interesting thing. Okay, so reflecting telescope, a little more history, it's like 80 years or 75 years after it was invented. The reflecting telescope was invented, and it was Isaac Newton, the same guy who did the laws of motion. And here's this word that I mentioned before, chromatic aberration, a rainbow halo, right? Why does it happen? Because the different colors focus in different places. They don't focus together. So instead of using a lens to gather the light, Newton used a spherical metal mirror, a primary mirror, to collect the light and reflect it to a focus. So there's a little bit of a complication because of, you know, if you try to collect the light, it turns out you try to bring it to a focus. If you wanted to put your eye there, you'd end up blocking the light. I'll show you in a minute. So he came up with a secondary mirror, which would bounce the light 90 degrees away from the original direction. And then a guy named John Hadley developed a different kind of mirror, which is parabolic mirror. And this is a little bit better than spherical, but now there's even a better one called hyperbolic. But anyways, these were just, they're two different kinds of reflecting telescopes, okay? So here are 3 different pictures that you want to be aware of, okay? So you could write them down. I might start with this one. This is the first one, the middle one, Newtonian. So if you look right here, what's the opening in the telescope called again? Anybody remember the name? The opening called the aperture, right? The aperture is at the end of the telescope. It lets the light come in. And then where is the light going? Well, it goes all the way to the bottom of the telescope. And at the bottom of the telescope is where we have the primary mirror. In all 3 of these pictures, the primary mirror is at the back of the telescope, right? The bottom of the telescope. Light comes in, and then it tries to focus it. Now, it actually, If you didn't stop it, it would come to a focus maybe out here, right around here. But in order to not put your head in front of the opening, Newton said, let me put a little mirror right here. Now you'll lose a little bit of the light that would have otherwise come in, but you bounce it out the side and you look at the light as it comes out the side. This is the Newtonian focus, right? So write down Newtonian, and you've got the primary mirror, bounce, hits the secondary mirror, comes out the back, out the side, sorry, out the side. A coude, I'll do this one second, use the secondary mirror, which was not flat, was slightly rounded. It actually did another little bending, okay? And then hit a third mirror and then came out the side. So you see this one has the opening near the front of the telescope, and this one has the opening near the back of the telescope. So if your telescope was very big, this would be much better. If your telescope wasn't very big, you could probably get away with this. That would be fine. And then finally, I want you to write down Cassegrain, because this is the telescope that you use, right? This is the Celestron 5SE. So if I ask you a question, or somebody asks you, what kind of telescope did you use? You first of all let them know it's a reflector, and it's a reflecting telescope, but it's a Cassegrain focus. How does that work? The light comes in, hits the primary mirror, bounces, then hits the secondary mirror, and that projects it back through an opening in the primary mirror to where the light finally emerges. Okay, so we'll have a name for this. This is called the visual back of the telescope, where the light comes out. All right. So actually, sorry, before I do this, I do have a little tiny thing that I could do for you. This is a small thing. It's not a big thing. It's a little tiny idea. But I do want to show it just because I have this thing I can show you. It's 3 different versions of just quick little things to show you. Let me start off with a refractor. And then I will do it again. Sorry, give me 1 second. I'm just getting it ready. Reflector, Newtonian. Okay, and then the last one, the Cassegrain. All right, so let's go back here. Okay, and I'm going to share my screen with you again. This time I want to show you our first one is a refractor. Oh, got a question? Sorry. Did you type a chat? Sorry, looks like you were trying to reach me. No? No, you're not. Okay. Sorry about that. Okay, back to the picture then. Okay, so this is a refracting telescope. And so the light's coming in this opening, and you're looking through this opening, right? So just very simple path. Okay. What do you call these 3-legged things that's holding it up? What's it called?
Tripod.
A tripod. A tripod, very good. And what do you call the little mini telescope that sits on the side? Anybody remember? Yeah, finder scope. Very good, finder scope. Okay, so that's our. What kind of telescope is this? A refracting telescope. Refractor. Okay. And then now, actually, can you help me out? Can you see this now? You see a different one? Oh no, it didn't work. Okay. Let's try it. It didn't work. I will show you. Okay, do you see this one now? Different one? So the light's coming in this opening here, and look at where the eyepiece is. It's way up here. And so you can look at the light, right? So what kind of a telescope is this, right? This is light comes in, hits the primary mirror, tries to make it to a point, but doesn't make it. It hits the secondary mirror and bounces out the side. This is a Newtonian telescope, right? Newtonian telescope. Everybody good? Newtonian?
Mm-hmm.
Okay. And then the last one is the one that we used to use, or we use, the Celestron. And everybody see it? Celestron looks a lot like our telescope. What's this little tiny circle in the middle? What is that? That is the secondary mirror, right? The back of the secondary mirror. So the light comes in, hits the reflector on the back, the mirror on the back, tries to come to a point, but doesn't quite get there, and then bounces back through the opening in the telescope. So this is the primary mirror, and here's the secondary mirror, and the opening is called the visual back, okay? The light comes out of the visual back, and maybe you remember there was a device that we put our eyepiece, connected the eyepiece in. Does anybody remember the name of this piece right here? Had a name. And you could rotate it to make it more comfortable. Anybody remember the name? Called the diagonal. The diagonal. Sound familiar? Diagonal. And then you look through the eyepiece right here. Okay. All right. So that is the telescope. 3 different kinds of telescopes. Okay. And let's go back to our slideshow. And I want to show you, okay. Does anybody want to buy a telescope? Anybody? One day?
I have one.
Oh, you have one. Okay, cool. All right. So, and I got to still ask you about where to go to Hawaii, because I didn't get to go to Hawaii.
Oh.
Talk to your son, but I'll get to go one day, maybe in the summer. Okay, so I want you to look right here. Those of you who don't have a telescope, one day maybe you want one. And I want you to ask the question, is bigger better? Okay, what should I buy? All right, so people ask me this all the time. So I'm just being proactive, and I'm going to give you some advice, okay? So first of all, if you have you know, a certain budget, you want to get a reflector, because for a given size, you can get a bigger reflector for your money. They're a bigger bang for your buck, right? And so the biggest diameter, so this is what I said, my advice, I would recommend buying the biggest diameter reflector that you can afford and you have space for, room for, right? Because you have to have a place to put it. You're not going to want to use it all the time, so you have to put it away, keep the box or whatever. But, you know, bigger is better when it comes to the primary mirror. Why? Why is bigger better?
More light goes in.
More light goes in, right? And what's the formula that you want to think about when you think about the size of the primary mirror?
Diameter.
Area equals pi.
Oh, yeah. Squared.
I.
Squared.
R squared, right? Pi r squared, okay? So bigger is better, right? But if you double the size, how much more light do you get? Double the size, what happens? Double. Okay, 2 squared is 4 times as much light. If you double the size of the telescope, you get 4 times as much light, okay? Now, magnification, do you want bigger magnification? Bigger is better on magnification, what do you think? No, and actually one of the signs that it's a bad telescope is when they tell you how amazing the magnification is. 200x, 500x, stay away, right? It's like totally a garbage. In fact, no one ever uses it. Somebody who buys a telescope with 500x, they try to use it one time, they get so frustrated they never use it again, okay? Because when you're using very high magnification, what happens to the field of view? What do you think? The higher the magnification, what?
Your field of view shrink, right?
The smaller the field of view. You can't see as much sky. So if you zoom in too much, then you can't really see very much, and it's really, really difficult to find anything, okay? So higher magnification means smaller field of view, which makes it difficult to find the object of interest. Stay away from telescopes that advertise really large magnification, okay? So that's just my very simple advice to you. But you can get a decent telescope for $400 or $500. Actually, you can get a used one for even cheaper than that, okay? So anyways, keep it in mind. Okay, so do you ever want to use high magnification? Is there any reason to use high magnification, or we just never use high magnification? What do you think?
I would think there's sometimes they're good for like.
I would say, why do we have the eyepieces if we're not ever going to use them, right? Of course, we want to use it sometime. So let me make sure you understand some reasons why you want to use high magnification. Number one, it makes it bigger, right? Is that good? Yeah, that's great. Makes it bigger. It's easier to see, right? However, there's some problems. When you try to focus it, you'll find out that you can't make the whole thing focus. Part of the image will be in focus and part will be out of focus. That's not so great, right? It's not necessarily bad. I put bad, but it's more like positive, negative, you know, it's not like pluses and minuses, pro, con, whatever. I put good and bad. I don't actually, now I want to change the words. It's not that bad. It's not the end of the world, but it's something to be aware of, right? You kind of think, oh, I'm going to zoom in. It's going to be amazing. And then you're like, oh, I can't see anything. And so the problem is, if it's a bright object, zooming in is not a problem. And, you know, for example, do you want to zoom in on the moon? Would it be kind of fun to zoom in on a crater or a mountain? What do you think? Maybe. Would you be interested maybe in trying to do that?
For sure.
Maybe you want to zoom in and see a little more detail, right? That's great. Or maybe a planet, right? To look at the details of the planet. But if you want to look at, or maybe if you want to look at some binary stars, right? And they don't look like binary stars, but if you zoom in enough, you start to see the two separate stars, right? You've been able to resolve them by using higher magnification. But then there's a third thing you want to make sure. So using higher magnification does make it bigger. There's a focus problem where not everything will be in focus, and the image becomes dimmer. Okay, this is a real problem. So what if you're looking at something that's very faint, and then you try to blow it up and make it bigger? What's going to happen? It'll become even dimmer, which means if you had a hard time seeing it before, now you have an even harder time. In fact, with many things like galaxies, if you try to make it too big, then you really stop being able to see any detail. Okay, so it actually is a little bit counterintuitive, but that's what I want you to be able to see, right? That the larger it is, the dimmer the light will be. Okay, so why would you want to use higher magnification? Well, binary stars, as I mentioned, planets, the moon. How about a single star? Do you want to look at a single star with high magnification? And the answer is, if it's a single star, it's going to be a point of light, and it's never going to change, right? Only the very closest stars can be seen with the largest telescopes in the world. You are not going to have access to that, not automatically at least. So if you are using a telescope to look at a single star, you just want to look at it, then use the lowest magnification you can, because that's going to be enough to see the star. If you want to try to zoom in and see that it's a binary, use higher mag. If you want to look at planets and their moons, use a higher mag. If you want to look at the moon in more detail, use a higher mag. Okay, so there's good reasons to use it. Okay, so not everything that we look at in astronomy is visible, right? We know visible light, Roy G. Biv, right? Roy G. Biv, I went the wrong way, okay? But in fact, in research, we often will use other colors of light that we can't see. So what other colors are there besides visible light? Other colors, what do you say? You can just read them right here. We have gamma ray telescopes. We have X-ray telescopes. We have ultraviolet telescopes. We have infrared telescopes. We have microwave telescopes. We have radio wave telescopes. We have all of them, right? So radio telescopes and visible light telescopes are found at the surface of the Earth. X-ray, infrared, ultraviolet, gamma ray, those are all going to be outside the atmosphere. Does anybody remember why? Okay, the answer is the atmosphere absorbs everything but radio and visible light. A very tiny bit of infrared makes it, but mainly it's absorbed. So all these other colors are absorbed by the atmosphere. So you can't put a telescope at the surface of the Earth. Okay, here are some examples of telescopes that you might look for. This is, I wanted to see this one. I was dreaming about it. The Mauna Kea pair of Keck telescopes. They're a pair of telescopes that give you, you know, beautiful. They're 10-meter telescopes. Does everybody get that? 30 feet across. Each mirror is 30 feet across. Can you imagine? The Kitt Peak in Kitt Peak, Arizona. This is the very large telescope array in Atacama Desert, Chile. And this is one of the largest telescopes in the world. Does anybody know what kind of telescope it is right here? A radio telescope. Is it the largest telescope in the world? Anybody? It is not. In fact, actually a really cool story. I think it's kind of cool. The Chinese have built the largest radio telescope in the world, just so you know. It's a little bit bigger than Arecibo, Okay, the largest radio telescope is in China. This is the largest one in the world. Okay, look at this. This is built into the a valley, you know, between some hills. This is the largest one in the world. How big is it? It is, it doesn't show you. It's about twice the area of Arecibo, which is in Puerto Rico. So how do they move this? How do you think they moved this? Anybody? Okay, that was a trick question. The answer is they don't move it. So what do they look at? Whatever is directly above the telescope. Okay, whatever is directly above the telescope, that's the interesting thing you want to look at, right? There's nothing else they can do. But it turns out that that's a pretty cool way to do the research. And so they're able to make lots of discoveries doing that. All right, let's see. But is that the largest telescope in the world? And actually, somebody said something, chat. How objective is what is the objective? This is actually, so radio telescopes are reflecting telescopes, right? These are reflecting telescopes. So this is a primary mirror. And they just wanted to make the biggest one in the world, right? So China is really interested in becoming the world's best at everything. And so they are producing more PhDs in every field than any other country on Earth. And at some point in the future, you're going to see more and more research come out of China that's innovative. Right now, I mean, even now it's already happening. Sorry, it's already happening, but you'll see it just more and more. In your life, you're going to see, I don't know how strategic it is. It's mainly just bragging rights. We have the biggest one. But there's a tiny little hanging receiver that goes above it. I can't see the detail here. But actually, if you looked at the Arecibo one, you could see that. I'll show you that one again. On the Arecibo, this is the secondary, which is actually, it's not really, it's more than the secondary. This is the eyepiece as well, the secondary / eyepiece. So this one, they don't use a secondary mirror, right? They just bounce it straight up to the receiver here. So this is actually where we're getting the signal right in the middle. Okay, so, but that's not the only kind of telescope. It turns out we have another kind called an array telescope. And it turns out that if you use an array of telescopes, they act as if they're a single telescope. And I have a link here. I have links to all of these, but I don't really want to go to all of them. I just wanted to put them there in case you were interested. I would like to show you something kind of neat, though. If you look at a telescope array, a radio telescope array, you can see some pretty cool. Let me go back to my thing here. Sorry. You guys are like, what are we showing me? What are you showing me? Let me go back to here. I know. Give me 1 second here. All right. There we go. Here we go. So this is some pictures of radio telescope arrays. And I want to look down on it to see, like this one. You see this? So they have like this triangular shape. And the idea is that these telescopes are linked together using electronics, and they act as if they are one, right? This is the key idea with an array of telescopes. They act like one giant telescope. So there's one giant telescope. And so if you make this larger, what's the benefit of making it larger? Well, you collect more signal, right? Collect more signal. But it turns out there's another benefit. And that is the larger your telescope, the finer the detail will be. Your resolution gets better, right? You have a smaller angular, your detail gets better on your telescope. So I would like to tell you that a little while ago, the largest telescope project that had ever been done captured an amazing picture. It's called the Event Horizon Telescope. Is a global network of synchronized radio observatories that work in unison to observe radio sources associated with black holes, right? So the reason you know about this is they captured the first picture ever of a, actually, you know what? I'm just going to look at the images because I think, oh, this picture actually shows me. Right here, this is the network of telescopes. So you see they have a network of telescopes. How big is it? And it's about half the size of the Earth, right? That's the effective size of this telescope, all working together. And that's why they were able to see this picture, right? This picture doesn't look like much, but it was taken of a telescope, I mean, of a galaxy, which is like 56 million light years away. I mean, it's really incredible. You just don't understand how amazing that is. This is actually the original image, right? So this is the center is what they kept publishing on the internet that you probably heard about. Okay. So anyways, how did you get the detail that you couldn't have seen ever before? From that network of telescopes called the telescope array. Okay. So a telescope array allows you to have effectively a larger telescope, as large as the array. Now, could we do better than they've done so far? And the answer is not much, a little bit, but it turns out in order to do much better, you're going to have to launch radio satellites up into space, and then they can become much, much bigger effectively. Okay, so that's the end of my slideshow. Okay, so that's the end of my slideshow. So that's the telescope lecture. You guys have a bunch of notes on telescopes. We are going to do one more activity. And again, this is to help you a little bit later. I'm going to finish by 6, by the way. So we're going to be done before 6. Okay. So you know your homework or your work is supposed to be on 22A. You're going to draw a track showing the position of Venus, right, wherever it goes. Okay. But can everybody turn to the front of your book? And I'm looking for, oh shoot, I wrote in this. Oh well. All right. Can you turn to page 00B? I'm going to cover it up in a second. I'm going to cheat. I gotta cover it up. I already wrote in this. I forgot I did this. I did it for another class. So, all right, here we go. I'm going to cover it up. Okay. So this is page 00B. Hold on, I'll show you the page. And, oops, wrong thing. Okay, here we go. Okay. Okay, so we're on page 00B. Does everybody see the picture?
Yes.
This is our, so what's the name? The real name is, actually, I'm going to tell you the real name. Schmidt dash Cassegrain. Do you remember the Cassegrain? Schmidt Cassegrain. On the front of the telescope, there is a plate, right? This is not on any test. I'm just telling you so you know what kind of telescope you were using. This is called a Schmidt corrector plate. And it makes the images get better, right? So it actually does something to get rid of certain light and makes the picture better, basically. Okay, so we have a Schmidt plate on the front, and then the light comes in, it hits the mirror, tries to focus, bounces, and goes back through the opening in the telescope. So that's the Cassegrain focus, right, that you're supposed to know, right? So this is a picture of our telescope, and I kind of like it because it shows you a couple details that I think you're really going to enjoy. All right, so we want to identify these parts of the telescope. So what's number one? Number one is trying to outline the full opening right here. What's the name for the opening of a telescope? Aperture. I see Grant mouthing it. Aperture. What is the word aperture? What does it mean, right? So you could write it in your own words. It would be the best if you write it in your own words. What's the aperture?
The area.
And the opening, right? It's the opening that lets the light in, right? Lets the light in, lets the light that will be collected by the objective lens or the primary mirror. Lets in the light. Okay, the aperture lets in the light that will be collected by the objective lens or the primary mirror. Something like that. Just write it in your own words. Okay. Okay, so number one. Okay, now Number 2. Okay, so now heads up, if you get stuck, it turns out that all of the answers are probably on the front page, almost all of them, right? Almost all of them are actually right here on the front page, okay? So on 00A. So if you get stuck, but I do want you to try to see if you can figure it out, right? Try to figure it out without looking at mine. Oh, I gave it away. Okay, give it away now. Okay, here we go. Number 2. What's number 2? So number 2 is this thing is right on the side, but actually it turns out it's this side too. It's actually the cylinder that holds it all together. Anybody remember what that was called? It's called the optical tube, right? The optical tube, right? What is the job of the optical tube? It
Hold
holds the
everything
telescope together. That's it. That's all I wrote. Holds the telescope together. Okay. So again, use your own words. It's better for you to define it for yourself. You'll be more likely to remember it if you write it in your own words. Okay. All right. So number 1, aperture. Number 2, optical tube. Number 3. What is number 3 showing us? It's right next to this. What is number 3? It is the primary mirror. Primary mirror. So what does the primary mirror do? What's the job of the primary mirror? To collect the light, to gather the light. Primary mirror, collect the light and reflect it forward. Oh, reflect towards. That's not forward. I can't read my own writing. Towards a focal point, right? Tries to make it go to a focal point. Now you can see from the diagram, it really should have been like out here somewhere, right? The focal point. But it gets blocked by number 4. What's number 4? Not the focal point, number 4, the secondary mirror, right? The secondary mirror. So the secondary mirror reflects the light from the primary. And in this case, it's a Cassegrain telescope. It goes back through an opening in the primary mirror. Okay, so number 4 is the secondary mirror. And you can see from the diagram that it's going back through the opening in the primary mirror. Actually, here's my opening in my primary mirror. Okay, number 4, secondary mirror. Okay, number 5 is one of my favorites. What's number 5? Can you see it from the picture? What is it?
The focus.
The focus knob. Yeah, that's the focus knob. I know, and you're like, why is that your favorite? But this is the cool, I'll tell you why. I really like this picture because it actually shows you something beautiful that most people have no idea what's going on, and you're about to understand what's happening, right? Can you see what the focus knob is connected to? It looks like it's connected to this vertical rod right here, right? This vertical rod, but that's connected to the primary mirror. And guess what happens when you turn the focus knob? Guess what happens? It turns a screw that makes this go back and forth. What are you doing when you turn the focus knob? You're moving the primary mirror. It makes the primary mirror move in and out, different directions, right? That's what you're doing. You're pulling it back or pushing it forward. And that, you didn't realize it, but that's what you're doing when you focus the telescope. Isn't that cool? That's why I like it so much. Okay, so the the focal focus knob, it moves the primary mirror in order to focus the image. Okay, something like that. Something like that. It focuses the light, right? Okay, so prime focus knob. Okay. How about number 6? Okay, so I alluded to this a couple of times, but you're supposed to know the opening in the telescope where the light comes out, right? The light is going to escape from the telescope body, has a name, okay? And you could look on that first page and probably find it. And I mentioned it a couple of times already today. It's called the visual back. So the visual back is this opening in the primary mirror that gets extended back to the back of the, it's really the opening in the back of the telescope. But the primary mirror has a hole in it, and the light emerges from the telescope in this opening called the visual back, okay? So number 6, the visual back, the opening in the back of the telescope where the light emerges. Something like that. Okay, so the light comes out of the telescope, and I don't know if you remember that sometimes when you look, actually I probably could find this. Hold on, let me see if I can find something. I'm just curious if I could find something. I'm actually, what if I find our telescope? Some images. Oh, perfect, okay. Kind of perfect, not perfect, but I want to do something like this. Okay, somebody's selling this for $4.97 plus shipping. Okay. So I want to look at this. This is somebody selling on eBay or something. Yeah, eBay, right? So if you take a look right here, there we go, something like this, right? You see how the back of the telescope, can you guys see this very well or not so much or not working? We made that big, but the picture's not much bigger. Okay. Oh, there we go. That's what I wanted.
That's
Okay.
bigger.
It's a little bigger. Okay. So you see how the telescope, the light comes out the back. If you tried to look right here, if the telescope was pointed straight up, there wouldn't be enough room for you to put your head here, right? So you really need this piece that connects to the visual back of the telescope. And the light actually bounces right off of this, right? And then goes out this piece here. So does anybody remember the name of this piece right here where the light is bouncing?
Is
Remember
that
that?
the
Look at the list if you want.
diagonal?
This is called the diagonal, right? And all it is a mirror that just bounces the light 90 degrees, right? So it goes this way and goes this way. And so it just makes it more convenient for you to use the telescope. It's really just for comfort, right? That's what it's for. So number 7 is diagonal. And what is it for? The diagonal. It bounces the light. What's another word for bounce? Reflects the light 90 degrees to make it more convenient to use the telescope. Can you guys read this, or you heard my words at least? I can't read this very well either. Although I can read it just fine here, but on the camera it doesn't show up very well. Bounces the light or reflects the light 90 degrees to make it more convenient to use the telescope. Okay, and then look at the picture again. What's number 8? The
Eyepiece.
eyepiece, yay. And what's the eyepiece for? We know now. The eyepiece. It makes an image, right? And if you change the eyepiece, what are you going to do? You're going to change the magnification. It makes an image, and changing the eyepiece lets you adjust the magnification. All right, so we got that page done. That's page 00B. I told you about telescopes. Oh, the last thing I do want to show you is if you want to review, what would be a good way to review? And so if I give it to you next week or the week after, it's got to be one not too far from now. If you go to Files, you can click on Study Guides. And you can find, okay, don't do this one. Oh, actually delete that. Oh, I can't. Oh man, I changed it. Oh, don't. Oh, you can look at that one if you want to see how much I changed it. But here's the review right here. Click this thing, and actually it's going to give you some information, okay? The aperture, magnification, field of view, optical tube, objective. It's not called the objective mirror. It's called the primary mirror. That's a mistake. Sorry about that. It's called the primary mirror. This is somebody else made this, and I haven't changed it. I should change it. Blah, blah, blah. Okay, and this is, we have this diagram already. A little funky. Somebody did this by hand though. It's actually pretty good. The focus knob is off. That's wrong. Just ignore that. Sorry about that. That looks funny. Okay, anyways, the keypad, right, on our telescope, the only thing that you ever touch. You never try to push anything else. How do we do alignment? Everybody remember? Auto 2-star. And the motor speed, blah, blah, blah. So these are some of the like key things to know about the telescope. Okay, all right. So yeah, so anyways, I think that's about all I have. Does anybody have any questions? Anybody have questions you want to talk about? I'll show you my face again here. I'm back. You guys show me your faces. I'm back. Anybody have any questions? Want to talk about telescopes? Anything?
Sean, I do. This is Erica.
Sure, sure.
In looking at all my notes, a lot of the stuff that we covered today, I know that I had them already due to another either lecture with you.
Yeah, maybe Earth 101.
I'm looking through my Earth 101.
It's chapter 4. Chapter 4 of our book talks a little bit about telescopes. But the detail is supposed to be a little bit more about the hardware here that's not going to be in your Earth 101 notes.
Right. And looking at the Earth 101, I mean, I did see the chapter 4 and read about that, but more of it, I don't know why I feel like I'm missing or saw or had.
What are you missing?
Maybe it's, you know what? I have a feeling that just from watching the crash course on telescopes and everything. I think that's probably what it is too.
Okay.
A lot of this sounded way too familiar to me.
Oh no, that's fine. Actually, that's great. That should be easier, right? It sounds familiar. You probably understand most of it. It's not meant to be really difficult.
I was knocking my head trying to realize where I heard it from.
Okay, good night. Yeah. No, don't worry. Yeah, you've seen this. You saw the crash course video. You saw chapter 4. And you've been using the telescope. That's the other part, right? You were using the telescope. So hopefully you learned, something from doing that as well. So yeah, don't worry. It's not meant to be really difficult. It's actually, it's if you study a little bit, you'll be fine. It's really not that hard. But there's a few ideas and the mathematical, yeah, go ahead, sorry.
No, I'm saying for me, I was worried because I thought I misplaced something that in other words, because it sounded so familiar, I thought maybe I misplaced paperwork or worksheets, but in going back now, no.
No, it's the first time that we've ever covered it in the lab. Yeah.
Okay.
Yeah, so we actually have a special, lecture for you to make sure you understand the theory behind telescopes. So this is a little more detailed than I did in the class, right? I mean, I don't think you saw some of this stuff in the class.
Not at all. Yeah, you're right.
Yeah. Okay. Well, good. Well, it's nice to see you guys and, hear you. And hopefully, that was clear enough. And then you just have a little exercise. So you're mainly take a quiz. You can take that quiz right now if you feel ready. And that will get you almost all the 2 points. And then the rest of it, just show me a picture of the track that Venus makes over the next month or so. And you put it on page 22A. Okay.
Perfect.
All right. Well, thank you guys so much. Have a good evening. Relax. Be safe. Try to do something special for yourself too. I don't know. What are you doing for yourself to be special, right? Kind of take care of yourself. Give yourself a time off or a little special time, relaxing time, reading or listen to music or take a walk. I mean, all those things are possible, huh?
Right.
Right. Okay, so I'll see you tomorrow for sure, huh?
Yes.
All right. All right, well, thank you guys so much. I'm going to go ahead and finish this for now, and I'll see you later. Take care.
Okay.
Bye.
Have a good one.
You too. Bye-bye.